Hello, does that work well? Work well? Work well? Work well? Work well? Work well? Okay, I think we could start. I hope everything works and you guys can hear me. Um, should be fine. Yes, should be all fine. Okay, quick introduction to me. I'm Felix, a PhD student at Imperial College at the Department of Mathematics. That's why I know Harry. We got in contact through the Students for AI Society. And I'm a research scientist at a company called Neural Space. We focus at the moment quite strongly on Bayesian deep learning, what I will also speak about today, and a given technique, what is called variational inference. And I will first give a very basic intro, some kind of motivation as well. Goes then into like the difference between deep learning and Bayesian deep learning. Then speak about variational inference. Kind of talk about a special technique, what is called Bayes by backprop, and then I will even continue and tell you what to do with that. In the end, there is like an example, because we at Neurospace implemented all that to analyze medical images, because it's quite good to have there that measure of uncertainty. So what are probabilities? Probability is just something that is uncertain. Basically an event, but we don't know how it will end. So we can have, for example, the weather forecast, and it is mainly the weather forecast is usually a couple of days ahead, so we don't know really what the weather is going to be. So we are kind of uncertain about the temperature, for example. So we must have ideally some probability distribution of the temperature for tomorrow, for example. In mathematical terms, we just say P, what is the probability of an event X, is always between 0 and 1, whereas 0 means it's absolutely impossible that it's going to happen, and 1 means it's certain that some event is going to happen. That event X could be, for example, temperature 17 degrees tomorrow. And directly connected to that is important to understand a random variable that is usually capital X, and that capital X can have small x's, which are the events. So we can have capital X as the temperature for tomorrow, and then x1 would be 17, x2 would be 18, x3 would be 19, and so on. And then for each of these events we have actually probability between 0 and 1. And when you sum all these probabilities together, you also get 1. So the sum over all small x's can never be larger than 1. Okay, so I already gave that example of the temperature. Let's say tomorrow, I just checked the weather today on my phone. It said 15 degrees and sunshine for tomorrow, London. What might come is that, right? So we have already quite often had that example. We expected a wonderful sunny day, in the end we walk in the rain. So would it really make sense that we have a fixed value, these 15 degrees and sunshine for tomorrow? Or wouldn't it be good if we actually say, hey, it's fairly likely, it's probably to 60% or 0.6 is the probability that it's going to be sunny and 15 degrees tomorrow, but there's also some probability that it's going to rain and we only have 10 degrees. Because we just don't know the future. Another example are medical images. So a doctor points out there might be a tumor in the chest, and he has probably long years of experience and has seen lots of these images, and then he gives this diagnosis what might he not be 100% sure about. So he need to give a diagnosis if the patient is healthy or not, and sometimes he is doing mistakes, and that would be quite painful because actually the patient might be actually healthy and get the wrong diagnosis. So it would actually be quite good if we have some uncertainties and not only fixed values. What means in the doctor's case a yes and no, or in the weather forecast a fixed temperature and an image that signalizes tomorrow is going to be sunny. Okay, so we keep in mind it's actually quite helpful for the predictions to have these uncertainties. So how do we incorporate all of that into deep learning? As you know, a deep learning is kind of simple model with some input x, some weight w, some nonlinear transformations g. We probably have a couple of these hidden layers here, and then we have an output, what is y hat, that's equal to just the nonlinear transformation of the weights multiplied by the input. And we do that a couple of times over the hidden layers, and in the end we have some kind of output. Then we recap here backpropagation. So actually how you learn something in a deep neural network, how you adjust the weights. We first of all measure the error. So we have some input and give it through the entire network and it puts something out. And that is sometimes right, sometimes wrong, depending on the y hat here. So when we measure the error, we actually measure the outputs, what is the y hat, the difference from the outputs, what is y hat, to the labels, what is y. And then we have some kind of cost function that can look different in different cases, but actually what they all do is measuring how wrong we are, or how many examples of a given batch were wrongly classified, and that gives us a number in total. What we then take to trace back to the weights which were responsible for that error. So we take the partial derivative of that cost function with right to each weight. Here we have just the weight 1, 1, what means the first weight in the first hidden layer, but we do that exactly for all the weights. So we update them, we multiply that partial derivative by a learning rate alpha. The learning rate is usually chosen quite small, something like 0.0005 or so, and then we take the weight value of the previous iteration and then update it to the new weight of after it has been calculated how wrong or how much responsibility it has for the given mistake. So we do that a couple of times over all iterations, over a couple of epochs, and in the end we minimize the error. So we adjust the weight values that they are closer to the values which give less wrong predictions. Okay, so keep that all in mind, and now we look what Bayesian deep learning is. The basic difference is that we have a probability distribution, what means these yellow lines here on the left side, whereas we have in normal, let's call it normal for now, deep learning models, we have these fixed values, what are, for example, 0.5 or 0.1. So we replace the fixed value with some kind of distribution that could look as the ones we see here on the left side. But how do we learn these distributions? There's something called, what is LRT, I like to call it, and that is the following. Usually we do take these probability distributions as normal distributions, what makes it just very simple to work with. And we have then not only one value, like in a normal neural network we have set 0.5 or 0.1, what is one value, but here we have now two values, and that is that theta, what is here on the first line. So we have a mu, what is the mean, like the average, what you can also see here on the right hand side, and we have a variance, what is the sigma squared, or we can take the standard deviation, what is just sigma. So yeah, these are the two values we want to learn for each weight. That is kind of difficult, right? Because when we do the backpropagation, we actually want to have one value for each weight, because we do that partial derivative, and then when we just replace that one value with two values, we just can't compute the partial derivative. So we have that trick here, what makes these two values kind of hiding in one value. That's actually pretty simple. So we define theta as these both values, mean and variance. Then we define a normal distribution, a standard normal distribution, what is the n01 here, and then we sample from that standard normal distribution, what gives us an epsilon. So, and then we have the weight, what we define as a function of the epsilon, what is then equal to the mu, the mean, plus standard deviation times that sampled value. So you can imagine when we do that sampling a couple of times, we figure out that it is actually a standard normal distribution. So from that perspective, then we can trace back what the mu and what sigma was for the distribution of each weight. Okay, and then how we actually update our weights is according to the Bayes rule. And you might have seen that in your probability class, maybe even in high school, but it's it's overall fairly simple. We have there probability of weight given the data, what is our interest, right? So we want to have the weights after we have trained the entire data set, what is nothing else as the left side of the equation here. And that must be equal to a likelihood, we call it likelihood, what is the probability of the data given the current state of the model. So you can understand it as how well is the current state of the model, what is the W, capable of reproducing the data that we have trained it with. That is what you can understand as a likelihood. How well the data actually, how well the data can be generated by the current state of the model. And then we multiply that by a prior and divide it by a data distribution. What is interesting here is that the data distribution is intractable. What means we just can't have all the images of one class. Let's take, for example, houses. I will bring later an example. Sadly, that also means that actually the variable of interest, what is the posterior, is then also intractable. So I will go in detail what intractable actually means. and that is just a really simple example. So we have a training set of whatever, let's say 100 classes, and one of these classes are houses. So we want to train a model with all these, let's say 600 images of houses, and then we want to go around London, take pictures of houses, and let have the model saying that this picture is the picture of a house. But the model has probably never seen that house before, so it must kind of generalize, and we can see this training data as a part of the probability distribution of the data, but it is just a part of it. So we kind of, with our training data, we can kind of approximate our data distribution, but we never know it for sure. We are never 100% sure that the data distribution looks like how we have it in our training set. And that means that we have a data distribution which is actually intractable. So to have to circumvent that intractability, we should have the entire data population P of D, what is in reality just not possible, because we would need literally of every house on that planet a picture. So let's get back to base rule just quickly again. We have the interactability here, but sadly we have the interactability of the posterior as well. So when we do then go on and kind of still want to have a posterior, we do something what is called approximation. There are some different methods how we can approximate. So we have a true distribution, what we don't know, but it is there. Like, just imagine a data set of all images of the house, so it is in reality achievable, but just intractable, not possible, not realistic in any kind of measurable time. And then we have two approximation methods, what are basically putting a variational distribution, that red thing what you see here in the middle, over the true distribution, or Monte Carlo, what means sampling from the true distribution. What we will focus on here is the variational distribution. That has a couple of reasons. The most important of all, you can read in my blog more, or you can read other sources about variational inference. The most important is that the Monte Carlo methods would be the other possibility, are very slow and very inefficient for complex data distribution, for complex probability distributions. And we have in neural networks usually quite complex and high-dimensional probability distributions, so it would take just too long, and we would not get, most likely would not get any good results with Monte Carlo. So it's just much more faster to take that variational. Okay, so remind yourself, we have that red distribution, put that on top, somewhere on top of the true distribution, and then we want to, we define that red one usually as Q, that is parameterized by theta, and that should be fairly simple, fairly equal to the P, what is the red one, what is the true one. But how do we make them equal? That is probably best explained by some kind of graphical intuition. So we have the total space of theta values. Theta, just to remind you, is the mean and the standard deviation, or the mean and the variance, and C theta defines the Q. So we have a total possibility how these two values could look like. And we have a p-value, a probability distribution, what is the true distribution that is somehow outside of that space. So we start somewhere where we initialize, maybe just a standard normal distribution, how I usually like to do it. So we just say mean is equal to 0, standard deviation is equal to 1, and then we see actually how close that is to the p. Most of the cases it's not very close, so we need to learn and go back and forth and go up and down, and have then that distance, KL means KL divergence, So that is kind of a distance between two probability distributions that we always measure by that KL. And that KL we minimize over time, and we finally arrive at some kind of optimal values for mean and standard deviation. And we still have then a KL that is just a minimum KL. So that graphical intuition we need to somehow translate in mathematical equations. What is done here? So we have that KL, what is defined as that integral. You don't need to look too much into details. I have that all in my blog, and you can directly read about it as some more details on all these mathematical equations. So actually what we all do is want to minimize that KL divergence, right? We just want to have a minimal distance between Q and P. What is said is that we have an integral here, and that integral is intractable because we can never know any integral 100%, right? It's always an approximation. So we have that intractability, what is again really hard to deal with. You can kind of rephrase that KL and can even further rephrase it and kick even some constants out, what makes it a bit easier. But overall, we have still that intractability. And this is basically what variational inference is stuck with. And then I will propose you now one possible solution how that intractability can be overcome, and that is based by backprop. So let's recap. We have a KL divergence that is intractable. So what we do with intractability is we always approximate. And what we do now here is combine that variational inference with Monte Carlo. So we, people call it Monte Carlo variational inference, but how it actually works is that we first put a variational distribution over the true distribution, and then our goal is still to make that red one very similar looking to the blue one. But since we can't really minimize that distance, that KL divergence, we take samples out of the Q distribution, out of the red one, which then makes it possible to have that minimization. And I will explain to you here now how that works. So instead of having that integral now, we have the sum, and that means it's tractable because we don't have that integral, what is basically an infinite long sum. We have that given amount n, what is how much we desire, maybe 20 samples we take, and then we just have the sum over these. And these samples we take from the Q distribution, because the Q distribution is the red one that I just showed in the previous picture, and this one wants to be very similar to the blue one. That's still the main goal. Okay, that was actually all what I want to tell you regarding variational inference and a little bit about based by backprop. There is then some stuff what you can do with it, and these are the two following kind of short introduction. There are some uncertainty estimations. So we have that variance, right? That is called here. The star means usually it's an unseen data example. So we want to have the variance of the probability distribution of a predicted class given the new input. So the predicted class is a y star, the new input is a x star. And that variance can be pretty easily decomposed into aleatoric and epistemic uncertainty. Especially on that point, it might be good if you will have some background reading later on these two different kinds of uncertainties. And there is one blog post that covers it quite well, in my opinion. Okay, just to give you a background what these two uncertainties are. There's aleatoric, what is caused by the dataset. So you can imagine if you have a dataset, let's say ImageNet, whatever, how many classes they have, more than thousands, I believe, and each class has not too many data examples, right? So if we look at houses again, we might have 600 images of houses, but the houses look very different, right? There can be a house somewhere in South Africa, but might look more like a hut, and there can be a house in in Canada, what is really built up and has maybe even grass on the roof or whatever. So houses can look very different, so the data that of these 600 images can be very different, still all belong to the same class. And that is captured in the aleatoric uncertainty, what is caused by the dataset. And then we have epistemic uncertainty, what is caused by the model. So it means that the model is actually not capable, or we have some kind of measurement how capable the model is to work with a given dataset. That can be very helpful, because we can see then when we have comparisons to other datasets, we can then see, besides the validation accuracy, what is of course the most important measure, we can see how uncertain the model is about the dataset. Okay, and then we have looked into medical images here, just as an example, as an application. These were kind of everything from MRI to X-ray to ultrasonic, and a couple of others we had as well, I believe. So we had the task of giving a model some 2D images of, actually we had a row of 2D images, because when you want to detect Alzheimer in the brain, you need to kind of, from every dimension you need to take images, and then they first come as kind of 3D images, but then you just need to slice them accordingly, and then you can work with 2D images. So what we did here, we were just saying that on the left, we were just asking the model which of these images has Alzheimer. And then for the left side, for the A image, we had then quite good predictions. Just an example was a probability that we have Alzheimer on the left side is 0.98. Then we automatically also get some uncertainty measures, what is very helpful when you then analyze these images. For example, the epistemic uncertainty was very low, so it means the model we used to analyze these images is good enough. But the aleatoric uncertainty was quite high, what means that the images, you can see them, they are quite in low resolution, and they might be quite different, because when we have that slicing done of these 3D images, we have sometimes, just imagine we slice at the forehead. The total brain is much smaller than the brain here, what we slice in the middle of it. So it was quite hard to work with. We can see here from the regarding the aleatoric uncertainty, but it still performed quite well. Then we also gave a task of locating the Alzheimer. We already knew that, or the doctors told us that Alzheimer's usually can usually be seen in these red areas, but we just wanted to make sure that actually the model looks at the right places, and we were quite happy with that it directly gave us examples where the model detects Alzheimer or not. Then we also worked with some malaria detection with the human cells, what was then actually quite an easy supervised learning dataset. What means parasitized, what means we have malaria, uninfected means we have none. Then we trained different models, also frequentist, what means just a normal neural network, not a Bayesian one, so just these normal point estimates as weights. And then we also looked at different data sizes. So what happens if we have the full dataset, what means 100%, what happens if we have only half of the dataset and only a quarter of it. And what was just totally logic is that aleatoric uncertainty automatically increases because we have less data, so it means the possibility, the chance that the images are more different when we have a smaller number of total images is kind of high. So it's totally natural and totally totally correct that the aleatoric uncertainty increases here. For the epistemic uncertainty, it also increases a little bit, but by far not as much as the aleatoric. And then we also have some chest X-ray that we analyzed, and then we first had that bounding box, and then also ask the network if in that critical space where the bounding box was set around, if it's likely that there is a like a lung disease or lung cancer or so. Yeah, I have also here some more references. I will upload these slides so you can have a look later on, and would for now just thank you. I would appreciate some questions if you have to. You are now welcome to ask in the group channel, or you are always welcome to send me an email or ask specifically in my blog post, because then it's kind of easy to follow up what you exactly need to know. And yeah, that was it for now. Would be more than happy to answer some questions if there are.